Okay, so hello everyone. In this video, we will cover process management in operating systems. So, in this video, first we will discuss process states, then user mode versus kernel mode, then process versus thread, and at last we will discuss user level thread and kernel level thread. So, first start with process states. First, let me clarify an important point. If we talk about in technical terms, the kernel doesn't actually know what process states are. This is a model created just to help us understand that whenever we start a process in our laptop, PC or mobile, what states it passes through from start to end. We have created this model to get an idea of how a process grows and moves from beginning to completion. Now, first is primary states. The primary states are mandatory states: new, ready, running, terminated, and wait and block. Other than these, there are some additional states that we will discuss later. Now, first is new state. New state means when we create a process. Creating a process means suppose you wrote a program in C language and stored it in a secondary memory permanently. Right now you haven't run it, just stored it. That's the new state. Or even when your operating system gets mounted in memory and background processes start running, that's the new states. There was no process before, but now we have created a new process, new state. Now, other than this, after new state, we have ready state. The moment you activate that process, it comes into the ready state or ready queue. Ready state means the process has come into the RAM, faster memory. Before that, it was staying stable in secondary memory, hard disk, but now it's in the ready queue. There could be many processes in secondary memory because we consider secondary memory very large. Like these days, laptop have 1 terabyte hard disk, but talking about RAM, we have 4 GB, 8 GB, maximum 16 GB. So you can't bring all processes into ready state. Out of all n number of processes, we bring only some into ready state. Who brings these processes? The long term scheduler. Its job is to bring more processes into ready state, which we call the concept of multi programming, bringing as many processes as possible into the ready queue. Now, the running state. After bringing processes into ready queue, we need to execute them. Every process wants CPU time to get terminated after execution. We dispatch or schedule some processes from ready queue to running state. How many processes we bring into running state depends on how many CPU you have. Running state means we are executing that processes by providing its CPU. In our current operating system syllabus, we assume a uniprocessor system. So out of all processes in ready state, we pick one and schedule it to the CPU. The process stays in the RAM, but its status change and it gets executed by the CPU. CPU executes all arithmetic logic and instructions one by one. Now, terminate state. When the CPU completes all the instructions, the process gets terminated. Terminate means deallocation. We take back all the addresses and resources we provide when the process came into ready state. Since we have limited RAM, we must utilize resources properly. But there are other cases. Suppose we shifted a process from ready to running state, but suddenly a high priority process came into ready state. We will give CPU to execute this priority process first, sending the process back to the ready queue. This happened due to two main reasons. First is priority. A bigger, higher priority process arrives. Second is time quantum. In round robin scheduling, each process gets a fixed time slot, as we discussed in multitasking also. The scheduler helping here is the short term scheduler, whose responsibility is to pick a process from ready state and send it to the running state. If CPU executes a process completely without interruption, it's called non preemptive. If we stop the running process in between due to priority or time quantum expiry, it's called preemptive. Now, what is preemptive and non-preemptive? It is clear. If CPU execute a process completely without interruption, it's called non-preemptive. If it stops and running process in between due to priority or time quantum expiry, it's called preemptive. Wait and block state. Suppose a running process want to read a file from secondary memory. CPU works in microsecond, but secondary memory is slow. If CPU waits for secondary memory, other processes will keep waiting. It's like a billing counter in supermarket. If someone goes to buy something else, while their bill is being processed, the billing person serves other instead of making everyone wait. So when a process request input output operation, CPU asks it to go to wait or block state. When input output is completed, the process doesn't go directly to running state. It goes back to ready state and wait for its turn. The medium term scheduler. Here comes the medium term scheduler. Handles swap in the and swap out operation when memory gets full. Now, additional states. In worst case scenario, if all processes in ready state request input output operation, the wait queue can get full. Since it's also in a RAM with limited space, we create a suspend wait state. Here processes are swept out to the secondary memory temporarily. Similarly, if ready queue gets full but a VIP system processes arrive, we create a suspend ready state, swapping some processes to secondary memory to make space. Okay, now the backing store in secondary memory temporarily holds these suspended process until the space becomes available in the RAM. So this is what these are additional states: suspend wait, suspend ready, and backing store. Now what is user mode versus kernel mode? Moving forward to user mode versus kernel mode. User mode, as the name suggests, when we as a user turn on our laptop and use applications, we are in user mode by default. In kernel mode, all core functionalities of operating system, major drivers, and system operation execute in kernel mode. The processor keeps switching between these two modes. Let me explain with an example. Example is file operation in Linux. Suppose I am using Linux and open a text editor to write a C program. When my program needs to read a file and write data to it, here's what happens: the file is on the hard disk, which is the hardware component. Okay, now this component is controlled by the kernel. Users cannot access hardware directly, they need the kernel. When the program executes and needs to read a file, it uses a system call, specifically the read system call. At this point, system switches from user mode, mode bit is equal to 1, to kernel mode, mode bit equal to 0. In kernel mode, mode bit is 0, and in user mode, mode bit is 1. System switches from user mode, mode bit number 1, to kernel mode, mode bit is 0. A trap interrupt is generating during this transition. System call executes, reads data from hard disk. After completion, system returns to user mode, mode bit again to 0 to 1. Now if you understand with the real life example, we can take a real life banking example. Think of a bank. You are in a user mode when you want to withdraw money. Bank clerk works in a kernel mode, like you can't directly access the money drawer, but you must fill a form and give it to through the window. They process it and give you the money. Whether you are listening to music, watching videos, or using Microsoft Office, application works in user mode by default. But when they need to print output on monitor hardware, they use system calls like printf, switching to kernel mode. This dual mode operation is crucial for system security and resource management. Now moving forward to process versus thread. Now what is process versus thread? Process heavyweight task, thread lightweight task. Process is a heavyweight task and thread is a lightweight task. We are talking about multiprocessing, multitasking environment where multiple tasks run parallel. To achieve this one CPU, we can either create multiple processor or multi-threading. Multi-threading is a particularly useful when the same type of process runs multiple times. For example, a print server receiving multi-print requests from different clients, same code executing multiple times. Process structure versus thread structure. Process creation: when we create a child process using fork system call, it complete copy clone is created, has its own data, its own code, its own stack and own register, uses different memory addresses. In process creation, when we create it with the child process with the fork system call, operating system treat them as a separate processes with different process IDs. Now what is thread creation? When we create thread with a process, all threads share the same data and code, but in the process creation there were different code and different data. Now in the thread creation, all threads share the same data and same code, but each thread has its own stack and registers. Thread share memory and addresses. Operating system consider the whole thread as a one unit. Now what are the key differences? The system calls. Process creation uses system calls like fork, but thread creation doesn't require any system call, it's handled at user level. Now memory uses. Process have different copies of data and code, creating overhead. If you write fork 3 times, you get 2 raised to power 3 minus 1 equal to 7 child process plus 1 person, like 1 parent, 8 total. Okay, now the thread share the same copy, creating less overhead. Now context switching. Process context switching is slower because you must save all values in PCB, process control block, with operating system help. Thread switching is faster, only register and address need minimal switching. Now blocking behavior. Blocking one process doesn't block another process, they are independent, but blocking one thread blocks the entire process because kernel doesn't know about the threading. User level responsibility. It is a user level or application level responsibility. This blocking difference is crucial. Processes are independent but threads are interdependent because they share memory and addresses. Now we have solved this problem in user level versus kernel level threads. So moving forward to user level versus kernel level threads. What is user level threads? It is managed by user level libraries like pthread.h in C. Applications responsibility to create them. It is applications responsibility to create user level thread. It is fast to create. It uses process calls and fast context switching. No operating system involvement here. And the problem here is, if one thread perform a blocking operation, like entire process gets blocked because kernel doesn't know about the user level threading. But in kernel level threads, it is managed by operating system itself. It can require system calls to create them. It is slower to create compared to user level threads, and context switching is slower due to operating system involvement. Advantage: what is the advantage of kernel level thread? If one thread gets blocked, other doesn't get blocked because kernel manages them independently. Now what is an important clarification here? Whether user level thread or kernel level thread, all threads share the same code or same data. That's what makes them threads. Now they have their own register sets and stacks, which is why we call them lightweight processes. Modern solution is what? Present system, we use hybrid environments like mapping multiple user level thread to kernel level threads using models like many to one, one to many, or many to many. Linux typically uses one to one mapping. You can see all running processes in Windows Task Manager, or use the ps command in the Unix or Linux system to view process information including process ID and execution details. So that's all about process management in operating system. So that's it for this video. We will meet in next video. Until then, bye bye.